stage is Jimmy Angelakis about using PostgreSQL with bibliographic data. Please go ahead.
Hello. This is a topic which doesn't appear often in FOSDEM, and it didn't appear in any of the recent PG confs either, because it's something that only librarians care about. Do we have any librarians here? More than I expected. Please do not be offended by what you will hear about librarians and their relationship with technology. So, this is going to be a mostly practical talk, and it's very hands-on. It's not very much about theory or the features of Postgres, and it's not even about the last version of Postgres. It should work on 9.4. But we're going to look at some ways to circumvent the monopoly that some companies have on bibliographic software, which some companies have perhaps 90% of the market share in libraries. And perhaps we can use Postgres to change that. With some hacker might start a project based on what he hears here, on what he hears here today, which might be good, and it might be something equally as bad as what we have now, because bibliographic software is generally bad. So what is bibliography? It's the study of books. It's become part of library, what we call now library and information science. And we have some types of bibliography. One is enumerative, which is the part we're going to be looking at today, which is basically cataloging the books that we have in our library and putting them into categories and topics. And descriptive is the part of bibliography and librarianship which deals with where an actual physical object is and what its attributes are. For example, that it's bound in leather, or it's the 3rd edition of 1979. So, how do we keep this data somewhere? We create bibliographic records, which is also known as metadata. And this is where the term metadata actually came from, and we started to use it in technological context and on the internet. So what do we keep for each book or whatever we want to catalog? We keep the name of the author, of course, the title, a subject heading, maybe some keywords. And this is all stuff that used to be written down on index cards, and now is actually available online on online systems, such as bibliographic databases. This doesn't mean that they're the databases we're used to. They're not just databases you can query with SQL, for example. Librarians have their own query languages, and they have their own formats, which might seem alien to us, but they make pretty good sense for their line of work. So, in the 60s, we started having machine-readable records. And the Library of Congress actually specified a format which is called MARC. And MARC is machine-readable cataloging, very imaginatively titled. And as it started being implemented in the 60s, you can imagine that it's not a technology that's made for the web. There was an attempt by the Library of Congress and some other groups to update the standard in 1999, and they called it MARC for the 21st century. So it's now MARC 21. On the next page, we'll see what their vision of the 21st century was. It's a very strange format. It's a text format with no delimiters that are actually usable. For example, it's not even usable as a CSV format. It's strange text with control fields and data fields which are different, and they're all titled by numeric codes. and you have to look up the documentation of the Library of Congress to find out what each numeric code stands for. And after the numeric code, we have indicators for each field. And the indicators modify the functionality of the field. So if you have an indicator of 1 or 9 before the field, it means something else. And then we have subfields. Subfields can be repeated inside a field. So you can have, for example, a field with the numeric code of 049, let's say, and it could have multiple subfields titled A. So this isn't a format we can really work with easily. And oh, did I mention that the white space has significance? So you can have strings which start with 5 spaces and have 10 more in the middle. And they all mean something. This is the lovely Mark 21 for the 21st century. And it starts with a header called leader, which means something. I have to make clear, I'm not a librarian, and I've only been playing with this for, I don't know, maybe 6 months. So if I say anything very inaccurate, please forgive me. So on the top we have the control fields, which don't have subfields. And then we have the data fields with these dollar signs, which signify that a subfield is about to start. It's basically indecipherable. It's not human readable. That's why they call it machine readable cataloging. And we can see some strange things here, such as that we have 3 instances of the 210 field, which is one of the title fields, according to Mark. So an attempt was made to make sense out of this format and bring it to something closer that we can use. And Mark XML was created. It's nearly as bad as Mark 21. The worst thing about Mark XML is it is a standard, but it's not being treated as a standard. So you can have commercial software which doesn't respect the format. And brace for impact. This is what Mark XML looks like. You have collections, which are subject headings, and inside the collections, and how do you know it's a subject? You have the ID up here, which is the subject heading, and inside them you have records which contain control fields, which are marked control field, and data fields, which are marked data field with the word data field. And you can see that there's a lot of wasted effort and wasted space here. And you have, librarians also care about the order of fields, which is bad for us, because as we'll see later on, our JSON B type doesn't respect order. So here we have a data field which contains 2 subfields, which should be in this order. Right here, it doesn't matter because one of them is subfield A and the other one is subfield 2. But if we had 2 subfields called A, then the order would matter, because you would be reconstructing the title the wrong way around. So let's put this aside for a while and look at what serials are. Serials are not numbers in this context. Serials are series of publications that are issued under the same title. So it covers academic journals, periodicals, newspapers, newsletters, and magazines, things that are published in a regular or irregular fashion and have no fixed end to their publication. So we can have them in electronic form as PDFs perhaps, or some other format, and we can have them printed as we have had for decades. Their basic identifier is the ISSN, which is, you know what the ISBN is for books, I guess. It's the equivalent thing for serials. So I work at the University of Edinburgh at a department called EDINA, which is a national data center for the UK, and it started being one in 1996. We just celebrated EDINA's 20th anniversary, and this department started as the University of Edinburgh Data Library in 1983. And one of their first relevant projects was Saucer in 1994, which was a web interface to actually search through the serials of the Scottish academic libraries, university libraries for publications. And the offspring of Saucer is SUMCAT, is the Serials Union Catalogue for the UK, which contains all of the serials published in the UK and has materials from 103 libraries, the National Library of Scotland, the National Library of Wales, and university libraries from the UK. Now, why is this important? This is important because you have to compile 103 different lists of metadata from libraries in different formats, which are not really compatible because every librarian uses MARC as he sees fit. So you have to have manual intervention before the creation of the MARC XML file. So to help this manual intervention, SUMCAT depends on some proprietary software and some open source software. The proprietary part is Ex Libris Aleph, and which has a huge market share in the library world, but it requires Oracle. And it doesn't even produce valid MARC XML. If a field is longer than it should be according to the developers of Aleph, then it gets truncated, and the XML gets truncated as well, even if you were in the middle of an attribute or a data field or a tag. So after the MARC XML is sanitized for use in SUMCAT, and how does SUMCAT use it? It uses a Solr database to index this whole thing, so you can search through the serials catalog of the UK. After that, the output, which is sanitized, gets fed into Zebra, a bibliographic database made by Index Data, which is open source. But it only has a few developers that actually understand what's going on under the hood. So it's not a very useful open source project for a start to base your code on. And it also functions as a Z3950 server, which is the query language that you have to use to find out what's going on inside this database. And Z3950 is a very old plain text protocol, which unfortunately is still being used and will keep being used until something supersedes it and gets adopted by the majority of libraries, which is not anytime soon. Some possible replacements are SRU and SRW, which are twin formats. One of them works as REST, and the other one works as SOAP, which means that nobody uses it anymore. Let's take a look at how Postgres can help us with this mess. We have the new JSON-B data type, which I'm not going to talk about because I think you've heard enough about it in the past few months. And we have the realization that XML and JSON can be interchangeable if we do some things like respect the order of the fields that we find. We also have GIN and GIST indexing, which allows us to perform rapid operations on our data without actually performing a full text search of the actual XML file or JSON, which would have been the case before this binary type. So I said, why don't we create a format which makes actual sense for insertion into a database? And let's create MARC JSON. I wasn't, of course, the first one to think of this, but the only reference is a blog post from 2010, and this guy basically tried it and said, yeah, well, I did it, but it didn't work very well because it didn't take into account field ordering, as we said, which we need, and it doesn't take into account duplicate tags, because in JSON-B we cannot have a tag named 001 and another one named 001 as well. So it kind of looks like this. This is the same data file we've already seen in Mark 21 and Mark XML. We define the control fields at the top as JSON tags, and the content remains the same, but in the case where we have a duplicate tag, we have every data field defined as a JSON array, so we can keep the order of the fields and we can keep the order of the subfields. So we have for tag, the problematic tag 210, which we looked at, we have multiple entries under 210, which can have their own indicators and their own subfields, and the subfields can also contain multiple subfields titled A or B or whatever. Let's look at what I used for this experiment, because as we said, this is a very practical talk. It's not really, I'm not really an expert on either bibliographic data or Postgres, but this is an attempt to make sense out of this chaos. So why not use PsychoPG? It's very easy to program for Postgres and Python. It's very fast because it's based on CPython. So it gives you the speed of actually something like you would get from libpq when writing in C. It's a very expressive combination. It lets you type something that looks reasonable, like English and not JDBC code. And you don't waste your time converting between object types, because it supports Postgres' data types as closely as it can as Python data types. You need very few lines of code, as we'll see some examples later on, which is very readable code. Now, the first problem is, remember that Mark XML file that we had? I was given a Mark XML file which was 24 unbroken gigabytes, which is not huge for some of the monstrosities you've seen, I'm sure, but it definitely makes DOM not practical, because I don't have 24 gigabytes of RAM to load it in. So DOM isn't really needed here, because we don't need to access the elements one by one randomly. We just need to parse through the file in order and just load it into a database. So we use what's called streaming XML, which is based on the old XPath library, which was one of the first, if not the first, XML library that was open sourced. And this is also known as event-based XML parsing, or simple API for XML, depending on the implementation. And I found a very interesting little library called XML2Dict, which lets you read through an XML file in DOM mode. And it basically gives you random access over the file, which is loaded, of course, in memory in DOM mode. And it gives you access in the form of Python dicts or dictionaries, which is very handy because it's almost like working with JSON. The formats are very similar. It's very fast, and it has a streaming mode, which we can use to avoid loading the whole file into memory. So, first of all, to start playing with this, the slides are going to be improved before it goes up on the web, so please forgive me. We installed, okay, I use Debian-based system, as we can see. and specifically Ubuntu because of the sudo. But looking beyond that, we can see that we need a virtual environment, so we can start with a clean environment to play with. We need Python development packages, and we also need the libpq packages in order to install CyclePG. We create, we create our virtual environment, which we imaginatively titled VE, and then our next step is to activate that Python environment and to upgrade pip. Excuse me. Because sometimes pip doesn't want to bring in the newest Python extensions, so you have to upgrade it from your distributions pip in order to get compatibility with newer Python eggs. So after we've brought in the latest pip, then we can pip install our library, XML to dict, which goes fine. And then we install CyclePG2, which will fail if you don't have the Python development libraries and if you don't have the development libraries for libpq. But here it doesn't fail, it just throws us some warnings, and it's successfully installed, so we can start using it. Let's see now, why do we want the conversion to JSON? Of course, we want to insert it into our database and play with our lovely JSON beat type. But we don't need to actually create a JSON file to do that. We can parse the XML in one go and insert it straight into the database using our Python dicts. I have to remind you that it's 24 gigabytes, which is 6.2 million distinct records. So the only thing we really care about here is throughput. And here comes the Python code. I apologize to people who are not familiar with Python, but it just goes to show you how few lines of code we need to do this thing, and how simple it is to connect it to Postgres if you haven't seen it before. So we define a CyclePG connection to our database, with our database being called Mark out of respect, and our user, which is also called Mark. We set our Postgres isolation level to read uncommitted so that we can insert quickly into the database. We create a cursor, some variables which we'll use in our loops, and a buffer which uses C-string.io, which gives you marginally faster operations than Python's strings. Now, since we said it's an event-based library, then we have to define callback handlers for the events that we find, where events are actual XML entities that we come across when we go through the file. So we write a handler, which, because I was bored, I defined all the variables we defined as global, and then we start going through the items, and so what it does is treat the XML file as an iterable thing, so it goes through items, and if it finds the leader that is the header that we talked about in Mark 21, it just outputs it. If it finds a control field, then it tries to see if it contains text and then outputs it, and so on. And if it finds a data field, then it starts going through the data field and combing through the subfields that we desperately need in order, and puts them in an array. That's all it does. And it's not many lines of code that you actually need. You just need the subcases And you need to also include the indicators that we talked about for each subfield. After that, what we need to do is just dump the output that we have, which is Python dictionaries, and we have to dump it into JSON format. But unfortunately, we have to replace the double backslashes with quadruple backslashes because it won't insert properly. That's a small problem. We have a basic loop here which tries to batch it into batches of 10,000 records. Of course, it doesn't work properly because you need another iteration of the loop here. You need to copy the code after the loop to take care of the rest of the records that are outside the 10,000 blocks. And that's it. So this is the handler function. It goes through the file and translates it into Python dict and outputs it as valid JSON. Now, the convert function just opens the file, and you will notice that we need to open it in read binary mode because we don't care if we are to treat it as text or Unicode or anything else. And we just send it to the parse function of XML to dict. We do keep our white space because we need it. We do keep our XML attributes because we need them. And we don't need to care about namespaces. And of course, we use the callback function that we defined just before that. And this is basically just so you can run it from the command line. And all it does is creates a table called sumcat with a single column called data, which is of the JSON-B type. And it does some timekeeping to see how long it takes. And basically takes a file name of an XML file and does all the work with it. Now let's say we ran this thing for maybe 3 hours on a desktop and went through the whole XML file, and we've got it loaded as in the JSON type that we defined on our database. So we can access the fields and the subfields, but we must remember that we have JSON-B arrays here. So we will not get the results we expect if we query with the arrow operator. So I do select data arrow 245 from sumcat, and I just need 3 rows. I don't want this to run forever. So I get our indicators for each tag, which is called 245, and I can see that I have a tag called subfields, which contains an array, which means that I can't access it directly, which means that I cannot index it, which is our basic goal here. So what do we need for indexing this mess? We need an immutable function, because when you try to index the fields, you will get an error saying functions and index expression must be marked immutable. So what's an immutable function? It's a function that doesn't modify your database, and it's guaranteed to return the same results for the same input. So we create a function called JSON to array, and it takes in our JSON-B data and 2 strings which describe our levels, and it selects subfield A, which we will only care about here, from the JSON-B array elements, which is a built-in Postgres function which unrolls your array. And then, as a second level, it grabs the JSON-B array elements from the big array, which is our tag. For example, 210, the tag with multiple instances that we looked at. And you have to name these, or else it will fail. And it all gets converted into text and returned as text. It's a simple SQL function. We don't need PLPGSQL for this. So, will it blend? Let's see what the function does. When we try to run the function, we select JSON array using these 4 subfields. Why these 4? 210, 222, 245, and 246 are subfields where you might encounter a title. They might also be empty, or they might contain string many spaces. So, in order to index them, we just concatenate the whole thing. And we can see that we get some results. So all we do is we tell JSON to array, our function, the column that it has to look into, and we tell it the fields to index, the fields to unroll so we can index. Now for text search, we use this thing called a TS vector, which for the English language does some stemming and throws out the suffixes of the words that we don't need and keeps the basic word roots or the stems. So we can see that the same results come up as Annuel Rapport, which is French, and Festive Magnus Program, background, Bolivia, country, and so on. So this is actually much more useful for our searches now. We can also look at the new extension called PG Trigram, which looks at, thanks Joe, which looks at trigrams, and trigrams are basically 3-letter groups of our string. And by comparing these groups, we can also compare strings and see how similar they are to each other. So it goes off the screen, ignore it, and we can see that it's broken down our strings into trigrams, and it's also taking care of the concatenation thing, which we don't care about. We need to search through all the titles. So how do we index? We just increase our maintenance work memory, because you don't want to do that with the defaults. It will take ages. So I give it a reasonably large amount of RAM to play with when creating the GIN index, which needs a lot of RAM. And why not 2 gigabytes? Because we only live once. We don't want to wait for ages. And for this to take effect, you have to restart the server. So we create our index, and it takes around 6 minutes to index 6.2 million records, which isn't bad for TS vector index. Our trigram index takes a bit more. It takes about, this is on a desktop machine, it's nothing fancy. It takes about 7 minutes to create the index on the fields that we care about, the title fields. And now we'll test them and see if this thing works. Sorry for the screenshots. This is going to become actual text in the final slides so that they can appear in search results and be optimal and so on. So we select our JSON-B array elements. What is 049? Our 049 in this case is the SUNCAT identifier. It identifies a single category of serials. So the American Journal of Psychology would have all its issues under the same SUNCAT ID. Then we grab the title field 245, and then we grab the rank. TS rank is a function which returns only the things that you're searching for, which in this case, by using plain to TS query, we just enter a string to search for. And this string has to be in the English language so that we can use the same stemming rules. And it says the American Journal of Psychology. So, our condition is to search for the string, the American Journal of Psychology, and we want an extra column called rank, which shows us how similar it was to what we searched for. And we get results like this. Some cat ID, the title, which in the first instance happens to be outside the 245 field. So we might find it in the 222 or 210, so it doesn't match when we do a select distinct. But we get very useful, accurate results here. And the rank is just a number, ignore it. It doesn't have to be 0.9 to match. So let's explain this, and we can see that we use the index here. It uses a bitmap index. It uses a recheck condition so that it matches our filter, and then it does the bitmap heap scan, which is even faster. It means it doesn't even go through the whole index, just throws out what cannot match on our index, which is basically the fastest kind of indexing performance you can get. The same query for our trigrams. Let's see why we would need to test for both. The first query would match everything that is relevant to psychology. But this will take care of misspellings. So if you misspell psychology, then it will bring you useful results. However, it will bring you also the American Journal of Pathology, which you don't want. So we need to combine both queries to make sure that we don't get any false positives. And we define the similarity that we require to be above 0.7 so it doesn't bring you any irrelevant results, which also delays our query. And we can see that the trigram query also uses a bitmap index scan and the bitmap heap scan. So it's also going to be fast. It is not as fast as the other one. But the combined query is fast because we've already thrown out the irrelevant things such as pathology from the TS query. And it just keeps getting bigger and bigger the more you look into it. And I've been told by librarians that there are also other fields where title might hide it. And so we get the same results when we explain this gigantic query as well. And why don't we write a lovely function to go with it so that we can just run the function with a string and it will give us back useful results. So let me see if I can run this as an example. Can you see the text? What did I call the function? Suncat query. So let's see. Remember, this is a 6-year-old laptop, and these aren't useful results, so let's change to extended display. And there you go. This is how this monster query function returns our results. We get all the 4 title fields that we look for, and in some cases they contain gibberish or just abbreviations, but we do get useful results. Why do we get useful results? We decided to give some weight to each of the algorithms that we used. So I'm using the TS query rank with the option 32, which brings it to the scale 0 to 1. And this is already in the scale of 0 to 1. So I just add them and divide by 2. And I will get something which is less than 1. So I hope I haven't confused you very much. This is my Twitter handle. You'll be able to find the slides here. And shortly, in the next couple of weeks, we will have the Adena developer blogs will become public, so you can see what we're actually working on for this project and other projects that Adena is working with relating to library and bibliographic data. And the slides are also going to go up on SlideShare. If I haven't bored you to death, I can take your questions now.
It seems to me that you explained this whole format change that is trying to be as much as possible reversible, so that you can go back to the original format, maybe minus some white space things.
Exactly.
And that you put that in a database, and that you then do, when you do the query, you have this monster query that every time you do a query, it's does this again, minus of course the fact that some indexing has been done beforehand.
This
what
is
is
an
the
example. It's not a really useful query for production.
Yeah, but what's the benefit to that compared to another approach that would be to try to do at insert time some number normalization over all the possible ways that mark can be interpreted, and then have your query somewhat
The thing is,
more changeable.
Thanks for the question. The data always changes, so you will get a different mark XML file every week or so. So you will have to parse through it and do inserts or updates or upserts into your database, which takes a very, very long time. But it's not really clear when you will receive the update. It might take a week, it might take a month, and you're basically using structured data, so you're not better off breaking it down into columns, because you don't know how many subfields you have, and you'll have the same problems indexing it as with the JSON. This just does it in 25 rows. Have I answered or gone around your question?
I think somewhat. You have answered it somewhat. I mean, I understand the fact that you get updates all the time, but I mean, most of the data will be just redoing, so that I still think that some normalization could help at the time that you really have a query.
You need it to be fully reversible, because you want Suncat also outputs the original Mark 21 field, which is reconstructed, because some librarians find it useful to look at the actual format, more useful actually than looking at plain text.
You mentioned that the XML file was corrupted. How did you correct it, or how did you sanitize the export from the upstream sources?
That's actually being taken care of before I get the XML file. And some people go through it by hand, if you believe it or not, and find discrepancies. And also you can see that when it breaks Zebra, which tries to index it, and when it breaks Aleph. So you can find out easily where the problems are in the XML data. But generally, yeah, there's software before that which produces the actual Mark XML file.
Are you aware of projects?
Hi, are you aware of projects like we do? I work for a small company that made a project for the French Bibliothèque Nationale, BNF. We expose several databases as ones, exporting using the semantic webs APIs. So we don't do this kind of stuff because we do import the data once or twice a year, something like that. We do normalization at the entrance. We do machine learning to try to prevent human interventions in these steps. Are you aware of this kind of projects, and how can they be related and interesting compared to what you're doing?
We can talk after this.
I'm not one of the developers of the project, so I'm not very aware.
No, I wasn't very aware of it. I was just looking at what Suncat was doing with solar, and they said you can only use solar to search through this data. I said no, you don't have to. You can also run a Postgres query which will return in something like 17 milliseconds. And this is what I was trying to prove here, that using a database for database related stuff is good. Thank you, I will look into that.
So, out of curiosity, you mentioned that there is this mark XML that is this monstrosity thing. Can you use actually XPath or something like that? Or it's just something like that looks like XML?
It has to be valid XML so that I can use the XML to dict library. You could write a parser for it, but why? You could also write a parser for Mark 21, and this is how ex-Libris made their money, but you don't want to do that. Sorry?
Yeah, like to go straight to a record instead of like parsing.
Yeah, but you will have to have it loaded somewhere. You will need 24 gigabytes of storage to go through the file.
I find the technical part of it quite interesting, but have you thought anything about how the ideal model would be if you were defining the data?
That could be the next talk. This is just, the experimental stage. Of course, you can use things like this to create interfaces. As we said, librarians have their own protocols and interfaces called SRU and Z3950, and you can use them to write Postgres extensions which can answer in these formats. So that is one conceivable way to go forward. So we could get rid of the middleware servers. Okay, thank you very much.